After reading through this module, 1. Water is the universal solvent of biological molecules which are studied generally in either solution or suspension. 2. Most experimental procedures in biochemical studies are dependent on the flow characteristics of biomolecules in water or aqueous buffers, which are therefore referred to as hydrodynamic properties, that is dynamics of macromolecules in a water based solution. The third outcome is techniques such as centrifugation, viscosity, diffusion, etc. are dependent on the flow properties of biomolecules and therefore are based on their interaction with water. Lastly, centrifugation analysis of macromolecules such as proteins and nucleic acids are used in preparative and analytical techniques to identify molecular mass and shape. Let me now introduce you to this topic. Macromolecular solutions are more viscous than the aqueous solvent they are dissolved in. The interaction of the solvent with the macromolecule has a great bearing in the flow properties of these macromolecules. Furthermore, the shape and mass of the macromolecule influences its behavior in solution. Solvated molecules have a water shell around them which makes them have a larger volume, sometimes referred to as the Stokes radius for globular or spherical molecules such as proteins. This water shell changes 1. The mobility of molecules in solution such as diffusion, 2. Viscosity, and 3. Sedimentation under a centrifugal field. In this module, you will be learning about the centrifugation technique, an important hydrodynamic technique, and its application in the separation and analysis of molecular weight. Let us now look at the equipment used in centrifugation and centrifugation analysis. A centrifuge is an instrument which provides a system for rotating a macromolecular suspension or solution at high speed, generating forces several times the force of gravity, resulting in the macromolecule being displaced towards the bottom of the tube or direction of the centrifugal force, a phenomenon which is called as sedimentation. Present in a centrifuge is a spindle which is rotated circularly by a motor. A tube housing body called rotor is placed into the spindle and rotates at the same speed generated by the centrifugal force which acts on the macromolecule to sediment it. Modern day ultracentrifuges can generate speeds of over 150,000 rpm, which therefore can generate relative centrifugal forces, also known as RCFs, upwards of 10 to the power 6 into g, g being the gravitational force equal to 9.81 meters per second square. Lower speeds cannot sediment macromolecules because Brownian movement prevents sedimentation. However, higher speeds overcome the opposing upward motions leading to sedimentation. A picture of a typical centrifuge and the effect of a centrifugal force on a sample has been illustrated. Picturized is a desktop centrifuge, which are nowadays very popular. You can easily see that there is a chamber just below the lid which has been pried open. You can also see a rotor in the middle which is actually anchored on a spindle. The various kinds of commands can be given on a panel wherein the speed etc. can be dealt with. The lid, when it is shut, can also cause the chamber to get evacuated, one feature which is essential so that the rotor can be run at top speed. Note that this is a typical ultracentrifuge, ultra meaning that it can generate very high RPMs and therefore also very high RCF. When a centrifuge spins, the suspensions around a centrifugal axis, a centrifugal force which is generated causes the suspended particles to collect as a pellet in the tube bottom. This is known as sedimentation. After the sedimentation or the centrifuge has stopped, the tubes containing the sample are gently removed and whatever has been sedimented can easily be recovered from the other part or clear solution, sometimes called as a supernatant. Let us see how, when a sample is being sedimented, you can actually analyze its speed and thereby come to various conclusions about its mass and so on. The force acting upon a macromolecule of mass m at a distance r from the axis of rotation and revolving with an angular velocity of radians per second, which is the term used here is omega, is the centrifugal force m omega square r. The opposing force or the force opposing the sedimentation is referred to as the buoyant force, which is equal to nu rho omega square r. Nu will be described later, but is basically the volume of the macromolecule. Rho is the density of the solution. Under the influence of both the centrifugal force as well as the opposing buoyant force, the net force experienced by the macromolecule is equal to Fs, which is equal to m omega square r minus nu rho omega square r, wherein Fs is the force of sedimentation, nu is the volume of the macromolecule, rho the density of the solution. The sedimenting macromolecule is opposed by the frictional force Fr, wherein Fr is equal to Vf. V is equal to dr by dt or the rate of sedimentation, and F is the frictional coefficient. Under the influence of the centrifugal force, the macromolecule accelerates till it is just balanced by the frictional force, or Vf is equal to m omega square r minus nu rho omega square r. The mass of 1 mole of the macromolecule is the molecular weight capital M, which is therefore capital M equal to mass N, N being the Avogadro number, namely 6.023 into 10 to the power 23. The volume of the macromolecule will be nu is equal to nu m divided by n, where nu is the partial specific volume of the macromolecule. Hence, Vf is equal to capital M into brackets 1 minus nu rho brackets closed omega square r divided by n. Substituting for sedimentation coefficient as V divided by omega square r, then S or the sedimentation coefficient is equal to V divided by omega square r, which is again equal to capital M brackets 1 minus nu rho brackets closed divided by capital N F. The sedimentation coefficient, which is a parameter of the macromolecule, is therefore the sedimentation velocity per unit force and is expressed in units of Swedberg or 10 to the power minus 13 seconds. Observe the table which indicates the sedimentation coefficients and molecular weights of some proteins. Myoglobin has an S or sedimentation coefficient of 2.04 and a molecular weight of 16.9 kilodalton. Ribonuclease has an S value of 2 and a molecular weight of 12.6. Chymotrypsin, a sedimentation coefficient of 2.4 and a molecular weight of 21.6. Fibrinogen, or the protein which is involved in clot formation, has an S value of 7.63 and a molecular weight of 340 kilodaltons. Diphtheria toxin, responsible for causing diphtheria, has an S value of 4.6 with a molecular weight of 70.4. What is obvious in the table is that the higher the molecular weight, the higher the S value. Let us now learn how the S or the sedimentation coefficient can be determined experimentally. The velocity V with which a macromolecule sediments can be determined using an analytical ultracentrifuge. The analytical ultracentrifuge has some distinctive features which has been diagrammatically or schematically represented. The rotor, whose photograph has been represented schematically as a part of the ultracentrifuge above, is basically a circular shaped body made of strong titanium steel and is placed within an armored chamber over a spindle which can be rotated at very high speeds by a motor. The enclosed chamber is evacuated as well as refrigerated, a prerequisite for a very speedily rotating object such as the rotor. The analytical rotor has two other important features. One, it has a sample cell as well as a balance cell. The balance cell only contains the solution in which the macromolecule is placed, usually a buffer. The sample cell has the protein or substance whose S value has to be determined. Furthermore, when the rotor is placed within the armored chamber of the ultracentrifuge, the sample cell is in such a juxtaposition that a UV light source can pass through the sample cell within the rotor, is bounded by transparent sides above and below, usually made of quartz or emerald, so that light can pass through. Light which comes from a UV light source passes through the sample cell and then is reflected by a mirror onto a detector. Therefore, the boundary of the sedimenting material, which has been indicated diagrammatically on the right side of the figure, can be easily located. The optics which usually are used to detect the boundary of the sedimenting material in the sample cell was initially done using Schlieren optics. This was initially used by T. Swedberg, who invented the analytical ultracentrifuge. However, nowadays more sensitive techniques based on UV absorbance are being used to monitor the boundary displacement with respect to time or V value. Using the sedimentation equation described previously, the molecular mass of the macromolecule can be determined. The determination of the frictional coefficient F and partial specific volume nu is described later. These are additional experimental values required for solving the sedimentation equation. Now let us determine the frictional coefficient and F and partial specific volume nu. In the previous discussion, two additional factors, namely the frictional coefficient F and the partial specific volume nu, were required in addition to the sedimentation coefficient S for determining the molecular weight. The frictional coefficient is difficult to determine directly, and hence the diffusion coefficient, which is easier to determine experimentally, is instead determined. D, the diffusion coefficient of a molecule, is defined by the Fick's law, which states that the number of molecules Dn passing through an area A in a time dt is related to the concentration gradient dC by dt by the equation dN by dt is equal to minus capital D A brackets dC by dt brackets closed. For molecules with larger frictional coefficient, the rate of diffusion is lower, and hence it can be shown that capital D is equal to K capital T oblique or divided by F, in which K is the Boltzmann constant and T the absolute temperature. In determining the diffusion coefficient of macromolecules, a boundary is created between a buffer and solution of macromolecules, and the spread of the boundary is determined with time. The frictional coefficient in the sedimentation equation can be therefore replaced as capital M is equal to S R T divided by D brackets start 1 minus nu rho brackets closed. Partial specific volume nu can be defined as the volume increment when 1 gram of macromolecule is dissolved in a large volume of solvent. This also can be stated that partial specific volume is the reciprocal of solution density. In other words, dV by dm is equal to nu, where dV is the volume increment per gram of macromolecule, or nu is equal to 1 divided by rho, where rho is the solute density determinable by simple techniques such as pycnometry. What is the significance of sedimentation coefficient or S value? We will now focus on this as well as applications of centrifugal analysis. The sedimentation coefficient of a macromolecule is generally normalized to S at 20 degrees and water, which is the extrapolation basically of S values determined at different concentrations to water or zero concentration. This is necessary because sedimentation rates decrease with a higher concentration of macromolecules, or in other words, the sedimentation value of a macromolecule is related to its concentration, because as more molecules or more macromolecules are present in a higher concentration of the solution, the macromolecules will impede each other or impede the sedimentation of others. The shape of the macromolecule also has a bearing on the S value. Long, elongated molecules such as fibrous proteins and nucleic acids occupy a larger volume in solution as they rotate compared to compact spherical molecules. Hence, spherical and compact molecules have a higher sedimentation value. Flexible molecules such as broken or nicked DNA, nicked standing for one strand is broken of the double stranded DNA, these tend to have a lower S value compared to rigid rods. One of the applications of sedimentation analysis is to determine the purity as well as study the aggregation of macromolecules. During sedimentation, macromolecules are displaced away from the solvent meniscus as a sharp band if they are homogeneous. Optical detection methods in the analytical ultracentrifuge would indicate one sharp peak if the macromolecular solution were homogeneous as indicated, or if aggregated as dimer or tetramer, more peaks would be detected. Observe the figure wherein you can easily see the peaks due to the monomer, the dimer and the tetramer. The tetramer therefore would have a higher sedimentation coefficient compared to the dimer and then compared to a monomer. The intensity on the y axis would give the relative presence of these various mers, namely monomer, dimer and tetramer, which would be useful to study the aggregation of macromolecules naturally or under certain circumstances. The association of virus coat proteins with DNA or RNA, typically in viral structures, or interactions of proteins with ligands and other molecular associations would therefore lead to larger molecular weight species and can be easily studied by sedimentation analysis. Another very useful application of sedimentation is density gradient centrifugation. Up till now, the determination of the S value required a technique called boundary method. The macromolecule is dissolved or suspended in a suitable buffer and then subjected to centrifugal force. Because of this, the larger macromolecule separates under the influence of the sedimentation force as a boundary away from the meniscus of the solution, and therefore this method was known as boundary method. However, another popular centrifugal method is the density gradient or isopycnic method. Here, the macromolecule or particle is layered onto a density gradient made up of an inert material such as sucrose or cesium chloride, and during centrifugation the particle sediments till it reaches a zone in the gradient which matches its own buoyant density, isopycnic, and then comes to rest. Note that sucrose or cesium chloride solutions, when subject to centrifugation, distribute through the centrifuge tube with a higher density to the bottom of the tube, followed by lower and lower to the top of the tube, and therefore a gradient has been created. The choice of the density gradient material such as sucrose or cesium chloride is based on the buoyant density range of the particles to be separated or analyzed. For example, the use of cesium chloride generates gradients between 1.4 to 1.7 grams per ml, which is suitable for the analysis of DNA and RNA, these having densities in that region. Quite clearly, what happens during density gradient or isopycnic centrifugation? Before the sample has been centrifuged, it contains the DNA sample distributed in the cesium chloride sample. So, these are all uniformly distributed. After centrifugation, the cesium chloride distributes, giving a gradient, higher concentration towards the bottom of the tube, less towards the top or the meniscus. The nucleic acids will now, depending on the range of densities which they possess, will come to rest at those points in the gradient wherein their buoyant density is matched. Another application of centrifugal analysis is in understanding the changes in conformation of macromolecules such as that of DNA. The more compact the molecule in general, the larger the S value, and the more disorganized the molecule, the S value would be lower. If DNA, which you know is a double stranded structure, is treated with enzymes or intercalating molecules such as ethidium bromide, the buoyant density would change, leading to variation in S value from the original. A compact DNA molecule would have a higher sedimentation value. However, when more and more ethidium bromide, an intercalating drug which goes and sits between the base pairs, is added, the DNA molecule would become longer and longer and therefore have more volume and have therefore a lower sedimentation value. Eventually, as even more ethidium bromide at a higher concentration intercalates, the DNA molecule undergoes a change, that is, it becomes more supercoiled. Therefore, originally when it was negatively supercoiled, it goes through a transition phase where the sedimentation value is low and buoyant density is therefore low, and then eventually becomes positively supercoiled. So, these conformation changes can easily be studied using the sedimentation or ultracentrifugal analysis. The way the ethidium bromide intercalates is indicated in this diagram. The DNA on the left, which is shorter, becomes longer and therefore has a higher buoyant or therefore has a longer appearance when there is intercalation. Another application is that when DNA bands, electrophoretic separation in agarose gels are often visualized for fluorescence by staining with intercalating fluorescent dye ethidium bromide. When the fluorescent molecule ethidium bromide intercalates within the DNA base pairs, the length of the DNA molecule increases and the buoyant density decreases, more volume for same molecular weight. The degree of intercalation can be studied by observing changes in the buoyant density as indicated. The DNA bands following centrifugation are visualized by using a fluorescent dye such as ethidium bromide. In general, isopycnic centrifugation methods are useful to separate particles of differing density such as the organelles of a cell, as well as study changes during experimental conditions in density. The picture shows how when cells are grown in the presence of heavy nitrogen, the DNA would have different bands corresponding to either having the lighter or the normal isotope, a medium which would have both the light and heavy one, as well as the heavy band which only is made up of the heavy isotope. Let me summarize what we have learnt in this module. Centrifugal techniques can be used to determine the sedimentation velocity V and sedimentation coefficient S, and hence is a powerful technique to prepare and study macromolecules such as proteins and nucleic acids. From the sedimentation coefficient S, the molecular weight of a protein can be determined. The shape of a macromolecule affects its S value, and this can serve as a handle to study effects of various reagents such as the intercalating fluorescent dye ethidium bromide into DNA. Density gradient centrifugation or isopycnic centrifugation is a powerful preparative and analytical technique used to study macromolecules.